Today we're diving into a real cosmic detective story. It's a story about how two of our best, most trusted ways of measuring the universe are giving us, well, two totally different answers. And this isn't just a small disagreement, it's something that's shaking the very foundations of physics. So let's get right into it.
Okay, so here's the central question. How fast is the universe expanding? Sounds simple enough, doesn't it? But it turns out the answer you get really depends on how you ask that question. And right now, the universe is giving us two completely different answers, and it's created a massive puzzle for scientists everywhere.
Yeah, you heard that right. Two different answers. When we look back at the early universe, we get one number. But when we measure the universe as it is today, we get another number, a much faster one. And look, this isn't some small rounding error. It's a fundamental, glaring conflict that honestly challenges everything we think we know about the cosmos.
So how in the world did we get here? How did we end up with two speeds for the same universe? Well, it all boils down to the two different ways we're trying to measure it. One method looks way back to the universe's infancy, while the other looks at how it's behaving right now.
Okay, so on one side we have the cosmic microwave background. The best way to think about this is like a baby picture of the universe. It's the leftover glow from the Big Bang. And from this picture we can run all the math and calculate how fast the universe should be expanding today. Then, on the other side, we have a totally different method. We basically point a cosmic radar gun at galaxies that exist now. We measure something called redshift. All that is a measure of how much their light gets stretched out as they fly away from us. The rule is simple. The more the light is stretched or redshifted, the faster that galaxy is moving.
All right, so when we look at that baby picture, the cosmic microwave background, and do all the calculations, we get a number. A very precise, very well-established number for the expansion speed. This is what all of our best models of the early universe predict should be happening.
But, and this is the huge but, here's where the problem starts. When we use that cosmic radar gun on modern galaxies, we get a totally different number. And it's not just a little different, it's significantly higher. So the universe today seems to be expanding way faster than its own baby picture predicts it should be. That discrepancy, that conflict right there, is what scientists call the Hubble tension.
So, what gives? I mean, is one of our measurements just flat out wrong? Or are we missing something really fundamental? Well, the source material we're digging into today argues for that second option. It suggests the problem isn't with our tools, but with a core assumption we've been making for almost a century about what redshift actually means.
For, decades, the entire field of cosmology has been built on this one really simple idea. Redshift equals speed. The more a galaxy's light is stretched, the faster it's moving away. That's it. It's been treated as a simple, direct, one-to-one relationship.
But think about it. That simple equation only works if you assume two things. One, that the vacuum of space is just a passive, empty stage for things to happen on. And two, that a galaxy's speed is the only thing that could possibly be stretching its light. The theory we're looking at today says, whoa, hold on a second. Maybe our understanding is incomplete. Maybe we've been missing a huge part of the picture.
So, what's the solution then? Well, this theory proposes a pretty radical shift in how we think about the universe. What if space-time isn't just a passive backdrop? What if it's an active, dynamic medium, a complete machinery that actually interacts with and influences light as it travels through it?
This new idea is called the fabric of reality. In this model, space-time itself isn't empty. It's an active player. It can interact with light. And if that's true, it means a galaxy's speed is no longer the only suspect responsible for redshift. Suddenly, there are other accomplices at the crime scene.
Okay, so this model says speed isn't the only thing stretching light. It introduces three hidden accomplices. First, what if the speed of light isn't totally constant? Imagine light traveling through a material that has a changing elastic resistance. Sometimes it's harder to get through, sometimes it's easier. Second, what if the particles themselves that are emitting the light are actually changing? Like they're contracting and changing their own frequency as the universe expands. And third, what if the fabric of space-time itself has all these unseen bumps and ripples that stretch light as it passes by, totally separate from how fast a galaxy is moving?
And this table really just breaks it all down. You see, in the standard interpretation, it's simple. The redshift you measure is the velocity. That's it. But in this new resonance model, the redshift we actually see is a mix of things. It's the velocity plus all these other weird intrinsic effects. So to get the real speed, you first have to subtract all the weirdness caused by the fabric of spacetime itself. So how does all of this actually solve the Hubble tension? It's simple, really. It completely changes what we think we're measuring when we point our telescopes at a distant galaxy.
And this is the absolute key to the whole idea. The redshifts we observe, it's not just one thing. It's a pie made of at least 4 different slices. The actual speed, what we call recessional velocity, is only one slice of that pie. The other slices, the weird light speed variations, the particle contractions, the space-time distortions, they've been there all along, hiding in plain sight. We've just been lumping them all together and calling the whole thing speed.
So what happens when you account for these other slices, when you properly attribute redshift to all 4 causes? Well, the part that's actually caused by pure speed gets a whole lot smaller. And just like that, the fast speed we measured with our radar gun comes way down, and it falls right into line with the slower speed predicted by the universe's baby picture. The tension, it just dissolves.
Okay, so let's recap the whole thing. The Hubble tension, it's a huge crisis caused by 2 measurements that just don't agree. The theory we've just walked through argues the problem was never the measurements, it was our oversimplified assumption that redshift equals speed. By thinking of space-time as an active, complete machinery with other ways to stretch light, we can fix our math. That high-speed measurement gets corrected, the 2 numbers finally match up, and boom, the cosmic crisis is solved.
And that leaves us with a pretty mind-bending final thought. If we've been misinterpreting something as fundamental as redshift for this long, if the very fabric of our universe is this dynamic, active, complex machine, it just makes you wonder, right? What else don't we see? What other huge cosmic secrets are hiding out there in plain sight, just waiting for us to finally ask the right questions?